Welcome back, everyone, to another deep dive. This time we're really going where few have dared to go before,
Ooh.
into the mind-bending world of quantum mechanics and special relativity.
All right.
Yeah. Now, someone sent us this really interesting book, A Quantum Ghost,
Okay.
and
I've heard of that one.
yeah, it dives deep into the whole idea of quantum non-locality,
Right.
that spooky action at a distance.
Yeah.
And and what really caught our attention
Yeah.
was the author's argument that a classical relativistic phenomenon called the relativity of colocality is
Hmm.
basically like a ghost of this quantum weirdness.
That's a bold claim for sure.
It is bold. So our mission today, if you choose to accept it,
Why?
is to unpack that argument and see if those parallels really hold up.
Right.
Who knows, we might just end up questioning everything we thought we knew about space and time.
I'm ready to get my mind bent.
Me too. Now,
Yeah.
before we get into the ghosts, we need to make sure we're all on the same page.
Of course. Of course.
So let's start with quantum non-locality itself.
Absolutely. This is one of those concepts that really challenges our everyday understanding of how the universe works.
It's like the universe is saying, you think you know how things work? Think again.
Haha, exactly. To really grasp it, we need to go back to the source,
Okay,
the EPR experiment,
right.
which throws a real wrench into our everyday understanding of cause and effect.
Okay, walk us through it. What makes this experiment so groundbreaking?
So imagine we have two particles
Right.
that are entangled.
Okay.
Now, entangled particles are linked in a way that even quantum physicists struggle to explain.
So they're connected, but in a way that's beyond our usual understanding of, like, physical connection.
Precisely. Now, imagine we separate these entangled particles by a vast distance.
Okay.
Miles, light years, doesn't really matter.
So we've got our spooky, entangled particles hanging out far, far apart.
Yeah.
What happens next?
Well, here's where it gets really mind-boggling.
Okay.
You measure a property of one particle. Let's say it's spin.
Okay.
The moment you do that,
Yeah.
you instantaneously know the spin of the other particle.
Whoa, hold on.
It's as
What are
if
these?
it's as if they've communicated instantly across that vast distance,
Defying the speed of light.
seemingly defying the speed of light limit.
Okay, how does the book address this apparent violation of the speed of light? I mean,
Yeah, that's the question that's baffled physicists for decades.
right.
One attempt to explain this was with the idea of hidden variables,
Okay.
which basically suggested that the particles had some kind of pre-existing information that determined their states.
So it's like they agreed on their spins beforehand,
Exactly.
and we just didn't know it.
Yeah, that was the thinking.
Okay.
But then came Bell's theorem,
Right.
which mathematically proved that this correlation couldn't be explained by any hidden variables.
Hmm.
It demonstrated that these particles are genuinely influencing each other non-locally.
So there's no sneaky classical explanation. These particles are connected in a way that transcends our usual notions of space and time.
Right.
Okay, so that's our quantum weirdness laid out.
Yeah.
But how does this book connect it to something from classical relativity?
Right.
I think you mentioned the rest principle earlier.
I did.
Can you explain that a little bit more?
Yeah, the rest principle is this fascinating concept
Okay.
that essentially states that every observer is fundamentally at rest
Yeah, rest.
within their own frame of reference.
So even if I'm like hurtling through space at thousands of miles per hour,
Yeah.
from my own perspective, I'm still at rest.
Exactly. It's a simple idea,
Okay.
but it has some really profound implications.
Okay, I'm intrigued.
Think about the Doppler effect.
Okay.
We never actually detect motion relative to ourselves, only relative to other objects.
Like when you hear an ambulance siren change pitch as it drives by?
Exactly.
Yeah.
That's the Doppler effect in action.
Okay, I see where you're going with this.
Yeah.
Our perception of motion is always relative to something else. There's no absolute standard of rest.
Right.
So how do we even begin to talk about things like colocality if everything is relative?
Well, to illustrate this point,
Uh,
the author uses a rather amusing thought experiment. He calls it the moose thought experiment.
Okay, I am intrigued. Lay it on us.
All right, picture this. Two cars,
Okay.
let's call them Albert and Bohr,
Albert and Bohr, I like it.
are driving along a highway when they collide with, you guessed it, a moose.
Poor moose. I have a feeling this isn't going to end well for anyone involved.
Well, the interesting part is how each observer perceives the event.
Okay.
Albert, Bohr, and even the moose.
Wait, even the moose?
Even the moose each see themselves as stationary.
Hold on, even the moose thinks it's standing still.
Exactly.
Okay.
And that's the key takeaway here. If
Okay.
every observer is truly at rest in their own space,
Mm.
then there isn't one single universally agreed upon 3D space.
Whoa.
The author proposes this concept of a multispace
Multi.
with multiple coexisting spaces.
Okay, the idea of coexisting spaces is fascinating.
It is.
How does the author reconcile this with our everyday experience of a single unified space?
That's where things start to get really interesting.
Okay.
And it leads us directly to the heart of the matter, the relativity of colocality.
Okay.
But before we dive into that,
Right.
let's take a moment to really grasp the implications of this multi-space idea.
Okay, are you ready to venture further down the rabbit hole?
Always.
All right, let's do it. Multiple spaces, each observer at rest in their own reality. That's a lot to process.
It is a mind-bending concept.
Yeah, but you mentioned this relativity of colocality being the heart of the matter.
Right.
So can we unpack that a bit more? What exactly does that mean?
Sure, colocality basically means being at the same place at the same time,
Okay.
but just like the idea of simultaneity.
Right, events happening at the same time.
Exactly. Colocality is also relative.
Hmm.
Different observers in different reference frames
Yeah.
might disagree on whether two events occur at the same location.
Yeah. So, back to our unfortunate moose.
Yeah,
Different observers like Albert and Bohr would disagree on exactly where the moose met its demise.
precisely.
Okay.
Each observer would place that event at a slightly different location
Right.
relative to their own frame of reference.
So there's no single answer to the question of where the moose died.
Exactly.
It all depends on the observer's perspective.
Right.
Okay. I think I'm starting to see the parallels to quantum non-locality here.
You're catching on quickly.
I mean, both involve this idea that our usual way of thinking about space and time might not be the whole story.
That's a great observation.
So what's the connection? How does the book tie these two concepts together?
Well, what the author is suggesting
Yeah.
is that this relativity of colocality,
Yeah.
it isn't just some quirky consequence of special relativity. It's a classical analog of quantum non-locality.
Wait, are you saying that we can see those spooky connections, those correlations without causation,
Exactly.
even in something as ordinary as a car crash?
Precisely. Think about it.
Okay.
In the moose scenario, the different locations of the moose's death,
Uh-huh.
in each observer's frame of reference,
Right.
they're linked,
Yeah.
but not because one caused the other.
So it's a correlation that arises simply from the nature of space-time itself.
Exactly.
But wait, wouldn't that mean that the moose dying in Albert's frame of reference is somehow influencing the moose dying in Bohr's frame of reference?
No, not at all. It's not about influence or causation in the traditional sense.
Okay.
It's more about a deeper underlying connection that
Right.
transcends our usual notions of space and time.
So it's a correlation that emerges from the very fabric of space-time,
Yes.
not from any direct cause and effect relationship. This is mind-bending stuff.
It is.
But the book takes it even further, right? It delves deeper into the parallels between these two seemingly disparate phenomena.
Exactly. And it's in those parallels that we see the true brilliance of the author's argument.
Okay, I'm on the edge of my seat here. Walk me through those parallels.
Okay, well, for starters,
Yeah.
both quantum non-locality
Yeah.
and the relativity of colocality involve this spooky connection
Uh-huh.
between seemingly separated parts.
Okay.
In the quantum world, it's the entanglement that links the particles.
Right.
And in the classical realm,
Yeah.
it's the fact that there's only one moose, one event, even though observers disagree on its precise location.
So the connection is there, even though it doesn't fit neatly into our understanding of how things should work.
Right.
What else?
Another striking similarity is that in both cases,
Yeah.
the correlated outcomes are not predetermined. It's not as if the particles or the moose
All right.
had a secret meeting beforehand
Okay.
and decided how they were going to behave.
So there's no hidden script,
True.
no predetermined destiny for these events.
Right.
Even though we know there's a correlation,
Yeah.
we can't predict the specific outcome in advance.
It's like with our entangled particle, we know they'll have opposite spins, but we don't know which one will be up and which one will be down until we measure them.
Okay, so there's an inherent randomness,
Yes.
an element of chance in both scenarios.
Precisely. And in both cases, the act of measurement or observation
Right.
plays a crucial role in defining the outcome.
That makes me think of the whole collapsing the wave function idea in quantum mechanics.
Exactly.
We don't know the state of the particle until we measure it.
Right.
And the very act of measuring forces it into a specific state.
You've got it.
Yeah.
And in the moose scenario,
Yeah.
we see a similar principle at play.
Mm-hmm.
There's no way to definitively say which observer's frame of reference is the correct one.
Okay.
The one that truly captures the location of the moose's death.
So to say where the moose really died,
Yeah.
we'd have to pick one observer's perspective at random.
Right.
Even though each perspective is equally valid within its own frame of reference.
Precisely. And that inherent randomness,
Uh-huh.
that lack of a single deterministic answer, that's another striking parallel between these two seemingly disparate phenomena.
It's like the universe is telling us that our rigid notions of cause and effect,
Yeah.
of absolute space and time,
Right.
just don't hold up at the most fundamental level.
Exactly.
Okay, so let me try to summarize this.
Yeah.
We have this concept of the relativity of colocality,
Mm-hmm.
which shows us that even in classical physics,
Yeah.
the idea of location isn't as straightforward as we might think.
Right.
And then we have quantum nonlocality,
Yeah.
where particles are connected across vast distances
Uh-huh.
in a way that defies our usual understanding of space and time.
Exactly.
And the author's argument is that these aren't just two separate, unrelated mysteries.
Right.
They're reflections of the same underlying principle,
Precisely.
a fundamental feature of reality itself.
It is a paradigm shift.
If you're right, this is huge. It's like we've been looking at these two pieces of a puzzle separately for so long.
Yeah.
And now this book is showing us how they fit together. It's changing the entire picture.
It is. And it opens up so many exciting questions.
Like what?
For example, if non-locality is a fundamental aspect of space-time,
Right.
what other classical ghosts of quantum phenomena might we find lurking out there?
Are you suggesting there might be other everyday occurrences that demonstrate the same spooky interconnectedness? I never thought I'd be thinking about car crashes and quantum entanglement in the same breath, but here we are. I think we need to dive deeper into the author's argument and explore some of those implications. Ready for the next level of mind-bending.
Absolutely. Let's do it.
So we've gone from spooky action at a distance to moose-related car crashes and even multiple spaces.
It's been quite a journey.
All in an attempt to understand this connection between quantum non-locality and this relativity of colocality.
Right.
It feels like we're standing at the edge of a very deep rabbit hole here.
We are. And it's a rabbit hole that leads to some of the most fundamental questions about the nature of reality.
I'm almost afraid to ask, but where do we go from here? What's the big takeaway from all of this?
Well, the author's core argument is that these parallels between quantum non-locality and the relativity of colocality,
Yeah.
they're not just coincidences. They're clues.
Clues to what?
They point toward a deeper connection between these two seemingly separate realms of physics.
So we're not just talking about some interesting theoretical similarities.
Yeah.
We're talking about a fundamental shift in how we understand the universe.
Exactly. What if those spooky quantum connections,
Yeah.
those correlations that seem to defy space and time,
Right.
what if they're not just confined to the quantum realm?
Yep.
What if they're woven into the very fabric of space-time itself?
So you're saying non-locality might not be just a quantum quirk,
Right.
but a fundamental property of reality, as described by relativity.
Exactly.
That's a pretty big what if.
It is. And it's a what if that has profound implications.
Like what?
It could mean that our current understanding of space and time is far from complete. It could mean that there are other classical ghosts of quantum phenomena
Right.
waiting to be discovered.
If colocality challenges our very notion of place,
Yeah.
what does this mean for our understanding of events and their interconnectedness?
That's a fantastic question, and one the book leaves us pondering.
Yeah.
It suggests that the universe might be a much more interconnected and tangled place than we ever imagined.
Wow, this deep dive has been a wild ride. We've taken on some pretty heavy concepts.
We have.
But I feel like we've come out the other side with a new perspective
Yeah.
on the universe and our place in it.
I agree. That's the beauty of exploring these big questions.
Absolutely. It challenges our assumptions and expands our understanding of what's possible.
Exactly.
To our listeners, I highly recommend checking out A Quantum Ghost.
It's a great read.
It's a mind-bending journey, for sure,
It is.
but one that will leave you with a profound sense of wonder.
And a thirst for more.
Well, that's it for this deep dive into the strange and fascinating world of quantum non-locality and the relativity of colocality.
It's been a pleasure.
We hope you've enjoyed the journey as much as we have.
Until next time, keep exploring, Keep questioning.
and keep driving deep into the mysteries of the universe.
Maybe you'll discover some ghosts of your own along the way.
See you next time.